Hello, dear. I would like to welcome you again to this session, which is a talk today. Wherever you are joining us from, we want to appreciate you so much for how far we've come since I guess you've done so well without wasting much time. We are very privileged to have, a very resourced personnel among us. I will not say much about her. I'll give room for her to tell you who she is and take us through today's talk. I thank you so much, Alexandra, for honoring our invitation and coming in today. More will be joining soon as well.
Thank you so much, Dorcas. It's so kind that you welcome me here. So this is my talk on optimization or optimization problems in physics, about keyboard problems, which are which is what I have seen so far, the most frequent field for quantum computers in use, and about how all of your life basically is one big optimization problem. So for my outline, I will talk a bit about the relevance, and then we'll talk about the two different sides, how computer scientists see the world and how physicists normally see the world in terms of computation. I will give you some classical optimization examples, which show a bit how physics has been used for optimization in the past. And then I will talk about quantum optimization problems. So, yeah, you can think, why am I giving this talk? I came here due to the one quantum program. Originally, it was advertised as a problem, as a talk about and a conference which normally focuses on diversity and inclusions, which in Western states normally means minorities and women. And I could think, yeah, why exactly am I talking about optimization problems? Well, generally, I am in favor of empowering everybody to live a life that makes them happy. And not only to understand nature, but also think about how we can use nature for our advantage. And the main reason why quantum research has been financed so far is that we think that first, quantum research can help us solve incredible problems. Most people think, yeah, okay. So normally when you go into the press, you see, yeah, quantum computing will help solve climate change. Quantum computing is calculating on exponential many states, solving problems that no one can solve, etc. And there are two things to that. First of all, in quantum computing, nature has been used to solve problems for centuries. So it is not that with the uprising of computer science and IT, people have been talking about solving problems mathematically, but the idea is very, very old. And using nature and physics to do computation is the oldest computing paradigm ever. So it has been used even in ancient Greece. The second thing with quantum computing is I looked a bit into the history why everybody is financing quantum. And the idea is that not only Shor's algorithm can hack cryptography, but normally the United States have been focused on thinking, okay, we need to invest into science and into science that can be used by the military to solve problems, to stay competitive in the global landscape. I think a lot about how the United States and Western countries have been dominating the world, which I don't want to judge upon. It's just that if you want to make, if you are looking for your research to be sponsored by somebody, look at the military. If you find a problem that is somehow related to military use, you will get sponsoring. And the second thing is that from military financing, mostly in DARPA, we have had the biggest innovation. And the US is hoping that this applies to quantum technology as well, which I have to admit we don't know. This is not completely true. The second thing is that right now we have a big AI boom with ChatGPT and Claude and everything else, and everybody is thinking about, okay, AI will exterminate humanity, that is bad, etc. But the true thing with AI is we have a lot of data, we have a lot of software, we have tons of old algorithms. AI algorithms are very, very old. They date back to the 1940s. They are as old as computing itself. But the reason AI is booming now and also quantum computing is booming now, it is because we have the computing technology. And the big thing about computing and computer chips is that as our life is very digital, whoever controls the chip technology and the next big thing in computing, in unconventional computing, is more or less controlling the future. The idea is, for example, Taiwan is it's a super small island. And the reason why the US is protecting it is not because they love Western values so much, because Taiwan is protecting Western values. That is not true. The reason US is protecting Taiwan, it is because some genius Taiwanese people have been thinking, okay, if we have a technology which is so important to the world that we can build a monopoly on it, then we can lure bigger powers into a contract that they have to support us. And this geopolitical thing is a big key in why states survive, who is sponsoring what, and why people invest into technology. And the thing with AI is that due to quantum physics, Moore's law is coming to an end. And now we are thinking about how we can build the hardware, really the chip hardware for AI. This is the biggest question in deep tech startups right now in computing in Silicon Valley. There are billions invested into NVIDIA. And physically, if we build chips smaller and smaller, which is the core thing, why Moore's law was successful, if we build more and more small, we will get to a problem because quantum mechanics will ruin it. You cannot build a discrete system with a discrete transistor who is either 0 or 1 if you come up to the quantum level. And we are already at the quantum level with computing. So making chips smaller is difficult. Also, we have a big discussion about climate change, which I will not go into. But if you use a physical system as a computing device, you are using physics itself. So it is also very energy efficient. This is one of the key points why people would invest into unconventional and analog computing on a large scale. Okay, now I will come to the Turing machine. So normally what I have seen in my life is that computer scientists normally think in terms of discrete mathematics. They think in terms of either zeros or ones. But physicists, on the other hand, think in terms of energy systems which can be controlled, a system which is controlled by forces, or by energy. And you can mold the system if you can couple it to an external energy source. If you can control the system and build can build a system which behaves in the same way, you can predict how nature itself computes. Normally, the fundamental model of computing is the so-called Turing machine, named after Alan Turing. And the idea is that the Turing machine is the ultimate model for computing. It comes from a time in the 1940s when computers just had tapes and were controlled by mechanics and everything. So the idea is you have a tape which can have either zeros or ones. You have you have a head which can either write to the tape or read from the tape. And the idea is that this can describe any computation in the world. So in theoretical computer science, you will go back to the Turing machine. And if a language is Turing complete, you will say, okay, this can do anything that any computer in the world is able to do. But now you can think, what about physical computing? What about nature? Is nature a Turing machine? Yeah, in the end, nature is a Turing machine, a quantum Turing machine. But maybe the Turing machine with its discrete levels and only thinking about zeros and ones is not the best model to think about computation in general. I would argue this also has implications for AI and for how to do neuromorphic computing. But that's another story. Okay. And now we come to optimization problems in physics in general. I will give some examples. Generally, you can think of nature, all of physics. If you combine all approaches from theoretical physics, you always get some sort of energy or force minimization. And depending on what you try to minimize, you can predict your system. So one idea is, for example, okay, let's say you are at some place and you want to build a new building. Let's say you want to construct, you are an architect, you want to construct a shiny new building for your city, and maybe your city head is vain, and your governor says something like, I want like something that nobody on this planet has. I want it to be extra unique, or you just try to find the best form to use the resources you have available. Now you can think of, okay, what material am I going to use? How much material do I need? And for that, you normally have to solve this differential equation depending on two coordinates, x or y. Normally in physics, you can also try to minimize the amount of coordinates by introducing constraints, but you still have to solve this differential equation. And it turns out that computers suck at solving differential equations. So depending on the complexity of your surface, this is super expensive, it is difficult. Doing it analytically is close to impossible. Doing it computationally is difficult depending on the computers you have. But on the other hand, you could just take some soap, some water, and a wire, which everybody has available. You just cut some wire in the shape, 1 or 2 dimensional, of the surface you want to have. This was like the first experiment that that I saw in experimental physics, and my introduction to experimental physics. Our professor would just take a spiral made from wire, like this one, tell us about optimization problems and the minimal surface problem, and just take the wire put it into some water with soap and just put it out, and the soap bubble takes the minimal surface. So whatever you want to simulate, just build an analogon of it in the physical world, put it into something you want to minimize, like the soap water. Think of a physical system that behaves in the same way, and you have built an analogy or an analog computer. For example, okay, you will not necessarily have a helix building, but maybe you have a building like this. You have these two wires cut in the shape of a circle, and maybe you have the distance, but solving analytically the minimal surface would be difficult. And by just taking some soap and some wire, you can solve simple and also more complex two-dimensional optimization problems with little to no effort. And the same paradigm is used in quantum optimization, which is like the key thing I would nowadays argue that NISQ computers are used for. Maybe another example, let's say you are in some city. I don't know. For curiosity, are you in a city where you need to build maybe a metro station or a metro network? Wait. So feel free to answer me. Who comes from a small city or bigger city and the metro network is maybe not so cool, and you don't know how to build a nice metro network? Or you have some stations where you have a lot of people and not the connections, and you want to find the optimum connection. Feel free to just raise your hand or say, yeah, okay, me. Maybe you come from a small city. Okay. Sorry, it's just I thought that maybe in Europe our metro systems are super old, so we have had them since the 1920s. But back then it was a difficult problem. They didn't know how to solve it. And actually it turns out, yes, you can do it by hand, you can take an educated guess, but you can also just take a petri dish and take some mold. So maybe you have old bread left somewhere, you just take the mold, you take some oat flakes and you put the stations on a minimized map of the oat. This, for example, here is Tokyo, the city of Tokyo, the capital of Japan, which is one of the biggest cities in the world. And if you would calculate this by algorithm, okay, for nowadays computers, this is not so hard because we have a lot of computing power. But if you don't have too much of computing power, going through every line which could search this graph is a bit difficult. No, you have algorithms like A star for it, but in general, that takes some time and some energy. The other possibility, if you don't want to waste too much mental space on this problem and you don't have a computer at hand, you just take some oat flakes. Here you have the potential stations where people live, and here you put the slime mold and you just wait. You just wait and wait and wait and see whether it can replicate the structure. And indeed it can. So the slime will automatically go, it will just extend in a circle form, because a circle is a minimal surface in 2 dimensions. And the slime will just look in all directions. And then it tries to eat the flakes. And if you wait long enough depends always on the system. You have some sort of intrinsic parameter for your system, which needs to be determined experimentally. If you wait long enough, after a certain time, in this case, 1 day, the slime has formed connections to the oatmeals, which are its eating resource, its food. And the slime has just established these connections, which directly mimic the Tokyo, the Tokyo metro map, which is quite intriguing because I bet that people who constructed that map needed way more resources and money to construct the map than just taking some slime, a petri dish, and some oat. Okay. So generally, if we talk about physical systems, these were just some examples. Generally says that you say, okay, you have a physical system. Normally in physics, if you try to solve stuff analytically, you take very simple systems and use them to approximate whatever energy surface or system you have at hand. But generally, you say, okay, a system is characterized by a state. You have an object which has a point in space and time at all times, and it follows a set of points, which is called a trajectory. And this trajectory is either driven by force or by energy. And you can derive the equations of motion either by using the force, that is just Newton's axiom, or you can use the energy. And if you use the energy, that will give rise to either the Lagrangian formalism or the Hamilton-Jacobi formalism, which is centuries old, but which is still used. And if you take the correspondence principle, you can see whether you can translate techniques from quantum control to classical physics and vice versa. Let's take a very simple example. I have a ball in my hand and I just let it fall down. In that case, the force is the gravitational force acting upon the ball, or just the gravitational field. So a mass is a source of the gravitational field. And in this case, the two masses, the Earth and the ball, attract each other. And as the Earth has much bigger mass than the ball will fall to the Earth and not vice versa. In that case, if you know exactly where my hand was in space and how much it weighed, you can, in theory, directly calculate the trajectory, which would be from my hand directly to the floor if I just let the ball fall. And you can use this. Idea. You do this normally if you work with liquids. In fluid dynamics, for example, if you have wind tunnels, they are all an example of what is called computing by analogy or analog computing. The idea is we take some small system which we can control, and then we let this system evolve over time. For example, if we want to build this big building or want to find the perfect map for the Tokyo area, we just don't want to go into Tokyo and build randomly. So we take a very small model which behaves, which will go along a physical trajectory to just find the shortest path it needs. And if we control all forces, we just check out the time evolution of our system. And then we have the optimal solution for our model. And this works for quantum systems as well. The the biggest thing I have seen in quantum computing so far is not Shor's algorithm. If you look at a lecture book, people always talk about Shor's algorithm, Grover's algorithm, and maybe HHL. For AI, HHL might be useful, but these are all algorithms which only solve certain problems. And you don't want to invest into a super expensive computer. I mean, quantum computers, they cost millions, if not more. You don't build a quantum computer just to solve small solve small factoring problems. For example, the biggest factoring problem so far, which has been solved, was 21 equals 7 times 3 with Shor's algorithms. We have the problem that for big quantum computers, in theory, we need error correction. There is another way as well. Feel free to ask me about that way. But generally, we don't have the error correction yet. We only have a few qubits. So people worry about the quantum winter. Yeah, nobody will found quantum research because we only have too few qubits. They want to see results. And when somebody tells you, yeah, quantum computing can solve climate change, quantum computing can solve, can cure cancer, find new drugs, whatever. Some of the problems are chemistry. I will accept that. Chemistry is a good use case. But most of other problems are optimization problems. For example, you want to optimize your traffic, like in the Tokyo image, in the Tokyo example with the network. Maybe you don't want to have the entire network, but you want to know the shortest distance or fastest distance from one node to another. For that, you normally use graphs. These are all graph problems, and they are very hard to solve. The same applies for network optimization. Portfolio optimization also belongs in that category. Protein folding also falls in that category. Attacking post-quantum computing algorithms. So right now, the NIST is doing a challenge for which algorithms are quantum secure, and as they only have computer scientists and mathematicians, we don't have a general proof that the algorithms are secure against any quantum algorithm that can be found. They can just secure against Shor and Grover's algorithm. Grover is a search algorithm which is optimal. So you can prove that with quantum search, you can only get a speed up of square root of n. So you can reduce the search size of a database from O from n, from linear time to square root time, but you cannot be better than that. But maybe for some problems, you want to be better than that. And most PQC algorithms so far are lattice algorithms. They work on a lattice. And ironically, these algorithms, they are known to be secure against attacks which find the discrete logarithm. So they are secure against Shor, but they are not necessarily secure against a quantum computer who does optimization. The idea why these algorithms are used is that all these problems are NP hard. NP is a complexity class. There are two kinds of complexity classes, time complexity and space complexity. But normally you say if an algorithm has polynomial space or polynomial time, it's easy. And if it's above polynomial, so exponential or something above, it is hard to solve. And this brings us to graphs and networks. So this is an example of graph. Sorry for this one. I had a problem with my slides because I introduced some slides before I gave this talk. So these are examples of graph problems. For example, if you have the shortest distance, you have a network like this one, or you can imagine all these points lay on a graph. You begin here, and maybe you want to find the shortest way to here. But maybe the shortest way, so normally we would say this is the shortest way by distance, but maybe going this way is faster because you get stuck in traffic around between these two nodes. In that case, this one would be much shorter. And to illustrate that, you can use a network, you can use a graph. You have so-called edges. The big dots here are edges, are nodes, and you have the edges, these lines. And you can also weight the edges, and then you can try to use either graph solving algorithms, or you can weight them in an analog computer. I will explain later how that works. So you have such a network. These are simple ones. In general, they are way more complex. And you want to solve network problems. All these optimization problems, including portfolio optimization, can be modeled to such a network. And in physics, this means you take a spin glass. So if you go into the literature and you read something like spin glass problem or Ising model, this one is the idea. So the Ising model was originally invented for magnetism, to describe how magnetism works. Normally, when all spins are aligned into one way, the system is ferromagnetic. And depending on how the spins align, a substance is either paramagnetic or not. And the idea is that you have these spins. So the angular momentum of an electron, you have electrons on edges, and the spin can point either up or down. And you want to find the minimal solution for these spins. You can also weight the spins, and you can control the interactions between these spins. So what you take is you take a physical system. For example, D-Wave does that. They just engineer a spin system which really has electrons on all these edges. And then they can control the spin of these electrons by applying an external magnetic field, which will align the spins into a certain direction. And by using this magnetic field and evolving the strength of the magnetic field over time, they can do computation. And this is how an adiabatic quantum computer works. So the idea is you have some initial Hamiltonian, which is easy to prepare. For example, applying a quantum X gate to all spins. And you have your optimization problem. The Zi are just the spin matrices on single qubits. And whenever you have this ZZ component, whenever you have a quantum gate with two matrices, you have entanglement. And in quantum computation theory and quantum information, we think that entanglement is the thing which gives rise to quantum computation's power. We don't know the specifics, so it is very hard to say in theory whether an algorithm is good or not. In theory, scientists still struggle to say, okay, we have this entanglement measure and we use this and that degree of entanglement, and can see whether the system, whether the system of the optimization problem is difficult or easy to calculate. If you want to benchmark a quantum computer, you can do this as well by just choosing random spins. You have coefficients here. If you choose them randomly, you can use that for benchmarking a quantum computer, for even seeing how much quantumness is in a quantum computer. And then you can try to heuristically see whether your quantum computer is better than classical algorithms, also quantum-inspired algorithms for like simulated quantum annealing. Normally, you have a scheduling function. You say, okay, the scheduling function f of t is 0 at the time of the beginning. And then you just let your system evolve very slowly to the optimization problem that you want to have. And the adiabatic theorem guarantees that if you evolve your system slowly, it takes you from the ground state of this easy to prepare Hamiltonian to the ground state of this Hamiltonian. So the Hamiltonian corresponds to the energy, and the ground state corresponds to the solution of your system. And the idea is, at the beginning, you only have this initial Hamiltonian. Then you choose the scheduling function and you let it evolve to this one. And the thing is that this is completely open research. Different optimization problems have different scheduling functions. And if you do this, you can solve, in theory, NP-complete problems. The problem is we don't know which scheduling function to take for the respective problem and how the hardware should look, and whether you can use symmetries. If you use symmetries, you can use tensor network techniques to solve the problem classically, but some problems cannot be solved classically. And the problem is we don't know how long the total annealing time will take. But we can try to add extra terms to speed up the annealing. And this is how nearly any quantum machine learning technique that I have seen so far works. You use this Hamiltonian, you discretize it, and then you update the parameters. You do a gradient descent to optimize the parameters in your circuit, and you hope it gives you your optimal solution. Every variational quantum algorithm works like that. To show it with an energy surface, you have this energy surface, and you want to go into the minima. And now you can ask yourself, okay, if I do quantum annealing, where do I have an advantage over classical algorithms? And the idea is that most algorithms which just go by the gradient, like gradient descent, can be stuck in local minima. For example, maybe this is your global minimum, which is the solution of your optimization problem. And maybe you get stuck here. In that case, you have a solution which is good, but not perfect. And you might want to have the perfect solution. And now you say, okay, if I'm stuck here and I heat up the system, I increase the energy of the system and I hope it relaxes. I am here, I increase the energy of the system along this scale, and maybe time evolution will get me to here. But you only have a certain probability for that. And if you have a landscape where you have very narrow peaks, where this is very narrow, so this is not the best figure for that. This is not very narrow, but if you have a very narrow and high peak, which separates the local minimum from the optimal minimum, then you can use the quantum tunnel effect. So quantum systems can tunnel through an energy barrier if it is of finite height, which close to any system is. Then you can use quantum annealing to travel from here to there. This is how the D-wave computers work. The problem is that quantum annealing, in theory, is as powerful as the circuit model. We have proofs for that. But quantum annealing and other techniques are completely heuristic. We don't know how good they are. So what we do what some startups, for example, where work Kipu does, is they try to speed up the annealing by coupling the system to an external energy source. And depending on the system, they add terms to the system to speed up this annealing process. And they do a discretization to map it to the circuit model. And with this, they get real speed ups, which is the only technique I have seen so far which is promising. Because error correction, the reason people do error correction is that most so if you are a big company or state, you normally want to found something that is proven to work. You want a technique where you know, okay, this technique will scale. But the thing is, in physics, we often use algorithms which are heuristic, meaning we don't know how they work, we don't know why they work, we use them because they work. And this is one of these heuristic algorithms. And I think this is the most promising so far. Using the annealing technique, because annealing is how nature itself works. It is how nature, which tries to optimize stuff, works in its theory. And then we can get to then we can try to optimize it by speeding up the annealing process. Okay. Some summary and outlook. I wanted to give some examples. Nature itself is one big optimization problem. You normally say, okay, you have an exponential phase space, but only a part of the trajectories are explored, which is why tensor network methods even work. And now the question would be, what is the separation between a classical analog computer, for example, and the quantum analog computer? So which of these optimization problems, they are all of this form, but depending on the coefficients, which coefficients do you need such that you really need quantum entanglement or the tunneling effect to take a quantum computer versus, for example, a classical analog computer? Because with a classical analog computer, you can do it as well. Maybe classical analog computers, they're called coherent Ising machines. Maybe they are a better alternative. Maybe they are a cheaper alternative. They are way cheaper to build. And maybe you can speed up the annealing process. These are some of the research fields and open research questions which are explored right now. And I would say these are the most interesting ones which are explored right now in quantum computation, because the rest, trying to get error correction, maybe to get error correction for some qubits, maybe it works. We don't know whether it works. And if the quantum winter comes, we have a problem. So I think this is definitely worth exploring. Okay, thank you very much. If you have any questions, feel free to ask. And I really encourage you to ask. Any questions? Yes?
Okay. Hello, I'm Wina Maduke.
Yes. Hi.
Yes. So the quantum error analysis, I understand that optimization of most systems is based on understanding and analyzing errors. So the quantum error analysis, how can you please elaborate further into it? Because it's like you brushed on it. Can you please elaborate more on that?
Could you maybe write the question in the chat, because I'm not completely getting it. You were talking about the error analysis.
Yes, please.
Okay. That is the big thing. Why? Maybe it's a bit personal. The reason D-Wave so far has not really seen big investments or adiabatic quantum computers is that we don't know error correction for them. We cannot do error correction on them. But what you can do is you take this adiabatic term here, and from the Hamiltonian, you can derive the annealing time. I can try to derive the annealing time. And I would argue if the annealing time is exponential in the system, then you have a hard problem. We don't know how the error scales in principle. So what Kipo is doing, they just add terms. They add some of the terms which you need to drive the system. Normally you would need exponentially many. What they do so far, they use the nested commutator approach. So they take the Hamiltonian commutated with itself times the scheduling function, and they only take the first term, and they do it completely empirical so far. We don't know which of the terms give you a good solution, so it is still an open research problem. We don't know how to do error analysis for this one, as far as I know.
Okay, thank you very much. So it
No
would mean
problem.
that in as much as we can't accurately determine which things are errors or not, is
We
there a
can
way?
determine whether there are errors if we
Mhm.
map the annealing process to a discrete to the circuit model. Then we can, of course, try to detect errors by using stabilizers. I think you are in my group, so I will tell you about stabilizers later. You will use them for graph states in our project, but you also use them for error correction to detect errors and to guarantee that your circuit is error-free or not.
Yes, please. Thank you.
Okay, sorry if I took too long with the answer. So you can discretize such a system with the Trotter discretization. You know how much error you introduce. That one you can not measure, but that you can estimate, because with the Trotter expansion, it is a Taylor series. And for the counter-diabatic driving term, for the CD term, you can also try to determine an error, but that you would need to do experimentally by benchmarking. Okay, thank you
Thank you
for your
very much.
question. Thank you. Other questions?
Please, can you go to the last part of the slide?
This one? Summary and outlook?
Yeah.
Mm-hmm.
I don't know, but I want you to show more light on the annealing part, how quantum computing is going to be important in annealing.
The idea is that you don't use a quantum annealer. You don't want to use a quantum annealer because we cannot do error correction on it. We take the quantum annealing model, so we take the Hamiltonian, we take the time evolution of the Hamiltonian, so we can solve Schrödinger's equation with the time evolution. It's just the matrix exponential of this function. We add some term here, and then the solution is the exponential of this big Hamiltonian. We discretize that part, and then we map it to a quantum circuit. Then we can also use error correcting techniques.
So can it predict maybe a particular time for the annealing process or something?
Interesting question. I am not completely sure, but I will note it. Maybe I can come back to you. In that case, I would have to ask. I bet there is a way. But in that case, I have to ask people at Kipu and maybe other researchers. But it would definitely be an interesting question. Can you just type your name in the chat, so, or just give me your Gmail address or email address?
Sure, I'll do that. Thank you.
No worries. Just put it in the chat. Thank you very much. Other questions? No? Then I thank you all for attending. Dorcas, could you send me the video of the presentation later?
yet. So when recording is ready, we'll share the link with you. We'll post it on the channel as well. So if there are no further questions, Alexandra, thank you so much for the wonderful presentation, for the insights shared as well. We really appreciate this dimension of quantum optimization, and also to know that it's so applicable to us, and we can find our roots there, get to take some research and do some activities there. So thank you so much for this presentation. And thank you so much, participants, for your presence and continuing support every time. It was great, and it's been a wonderful day. I mean, for all of us today, for this talk. Thank you so much. We'll continue updating you through email and through your WhatsApp. But then the update is that very soon all groups will be presenting what they are doing so far on their projects. We'll update you on the date and time for that. So we are urging that all groups prepare. So I mean, to brief us on what they have done so far, please. So, and the other thing as well is if you need any kind of information, any kind of assistance, we urge you to kindly use the email and not personal WhatsApp messages to us. Kindly use the email and we'll address all concerns through the email you send to us. Thank you so much. And you can connect to Alexandra on LinkedIn. She's on LinkedIn as well. Is it possible to share your LinkedIn profile with us, Alexandra, so that maybe our participants can just click on it now to connect with you, if it's okay with you for now. If not, you can.
I just posted my LinkedIn to the chat. Feel free to connect with me.
Okay. All right, great. So please kindly connect with her, share your experiences as well on today's presentation on LinkedIn, tag her, tag Elias, tag us, and tag your colleagues as well. Thank you so much, all of you. So we'll give you some few minutes to click on the link and all that. Maybe I'll copy and also share with you in the WhatsApp pages as well.
Perfect. Yeah.
All right, Alexandra, thank you. We hope to have you next time, maybe not online, for our physical activities and all that next year. We hope you can come down to Ghana to meet our participants.
That would be awesome. I would love it. Yeah. Thank you so much, Dorcas. Thank you, dear participants, for participating, for listening.